Okay, welcome back. So, in this lecture I am going to talk about few inequalities which we are going to use a lot during this course of this lecture. So, in particular I am going to talk about these four inequalities. First one is Jensen's inequality, which talks about whether a function is concave or convex. Then we talk about what is known as log sum inequality, and we will see an application of this inequality. Subsequently, I will talk about a lemma called data processing lemma, and finally, I will talk about Fano's lemma, which links probability of error to basically uncertainty in knowing a particular bit. So, these are the four results I am going to show you now. So, I start with Jensen's inequality. So, function is concave over a non-zero interval I if for each point x naught which belongs to this interval there exists a real number c such that this relation holds. So, just look at, let's draw a function. So, let us see, this is my y axis, x axis. If I just draw a function like this, okay, is this a concave function or a convex function? It is a concave function. So, you can see basically, so if it is concave over, let us say this interval I, so there exists a point for each point x naught which belongs to this interval over which it is concave, there exists a real number c such that f of x is below f of x naught plus c times x minus x naught. So, let us just take a point, let us say this is my x naught, this is my x naught. So, f of x naught will be this one, f of x naught plus c times c minus x naught. What is c x minus x naught? It is a line passing through x naught. So, I can always draw a line passing through this x naught. So, this will be my f of x naught plus c x minus x naught, correct? And you can see for a concave function you take any point, let us take this point, let us say this is my x naught point, then I can draw a line like this, this is f of x naught plus c. If I take this point I can draw a line this, that is why I said this c may depend on x naught. So, if I choose this my slope is this, if I choose this my slope is this, if I choose this my slope is this, but over this interval where it is concave I can always find an x for all x naught this relation holds. Okay. So, if this function f is concave over this non-zero interval for each x naught which belongs to this interval there exists a c, the value of c may depend on what is my x naught such that this relation holds. Okay. Similarly, I can define for convex function, this would be f of x will be greater than equal to this. Now, Jensen's inequality says if the function is concave and if x is a random variable taking values in this interval over which the function is concave, then this relationship holds, which is the expected value of the function is less than equal to function evaluated at expected value. Now, can you tell me how can I derive this from this? I will take the expectation on the both sides. If I take expectation here, I will get expected value of f of x. Now, what is the expected value of f of x naught? This will be f of x naught because that is a constant plus c times expectation of x minus x naught. Now, how do I get this form? I will choose my x naught to be expected value of x. I can take that because x naught lies in that interval over which the function is concave. So, I can take my x naught to be equal to expected value of x. So, if I choose my x naught to be expected value of x, then what is going to happen? F of x naught will become f of expected value of x. This was c times expected value of x minus expected value of x, that will be 0. So, I will get this relationship. Okay. So, from here I get this by taking expectation and choosing x naught to be equal to expected value of x, which I can choose because x naught is a value inside that interval x over which the function is concave. Okay. So, this is known as Jensen's inequality. So, Jensen's inequality says if a function is concave and if x is a random variable taking values in I over the interval over which it is concave, then the expected value of the function will be less than equal to function of expected value. Similarly, we could define when a function is convex, in that case this will be greater than equal to sign. Now, I can use Jensen's inequality to get this result. So, function f is concave over this interval I if and only if for every x1 and x2 which belongs to this interval I over which the function is concave, this relation holds. Okay. For lambda lying between 0 and 1. Now, how can I get this from here? Jensen's inequality says expected value of f of x is less than function evaluated at the expected value. So, here x takes two values, x1 and x2. Let us say the probability of occurrence of x1 is lambda, then what is the probability of occurrence of x2? 1 minus lambda. So, then what is the expected value of the function? It will be lambda times f of x1 plus 1 minus lambda times f of x2. So, what I have here is expected value of the function, and what did you have on the right hand side? Function evaluated the expected value. So, what is the expected value of x? Lambda of x1 plus 1 minus lambda of x2. So, this is what I have said. Take a random variable x which will take values x1 and x2 with probability lambda and 1 minus lambda, and using Jensen's inequality, function of expected value will be this, which should be less than function expected value. So, this. The function has a second derivative that is non-negative over the interval, then the function is convex. That is another way of doing it. So, I have shown you 4 different ways. This is how you can show whether a function is concave or convex. This is how you can show whether a function is concave or convex. You can show it this way, or you can take the double derivative if it exists and see whether the function is concave or convex. So, if I ask you to show that whether a function is concave or convex, you will see one of these 4 ways is suited for a particular problem. So, let us take an example. Let us use Jensen's inequality to show appropriate inequality between these two functions. Expected value of this function e of minus ax and e of minus a expected value of x. So, this is basically we are taking expected value of a function and this function expected value. So, we need to find out how does the function behave. What is the function here? It is e raised to minus ax, and in this case the function is under root of x. So, if we take the second derivative, that comes out to be positive. So, that is convex from the definition that we had. So, that means if it is convex, then expected value of function will be greater than equal to function evaluated at expected value. So, that is the relationship here. Similarly, in this example, second derivative comes out to be negative. So, the relationship is expected value of function is less than function evaluated at expected value. Okay. So that was my Jensen's inequality, which basically tells us whether the function is concave or convex. You will see its application in subsequent lectures. Now we are going to talk about what is known as log sum inequality. So what does log sum inequality says? For any non-negative numbers a1, a2, a3, an and b1, b2, b3, bn, let's say, such that summation of this ai and summation of this bi is bounded, then ai log ai by bi summation over all I is greater than equal to summation ai log summation ai by summation bi. So let us prove this result. So I am defining ai dash as ai divided by summation of ai, and similarly I am defining bi dash as bi summation of bi's. Okay. And I am finding the divergence between ai dash and bi dash. Now from the result that we have proved, the divergence between ai dash and bi dash would be greater than equal to 0. So this is from the definition of divergence between ai dash and bi dash, and this is greater than equal to 0. We have already proved this result, right. Now we plug in what is ai dash and bi dash. So ai dash was ai summation this ai's log ai summation of this ai's divided by bi summation bi. Now what I am doing is I am taking this summation out, okay, and so I have summation ai, and now I can write this as ai by bi, and I can have minus of log of summation ai by summation bi, right. So I am getting ai by bi summation ai, and then again summation ai minus log of summation ai bi. Is this clear? Now what can you say about summation ai? I said they are non-negative numbers, right. The summation would be positive, right. So this is positive, so then I say this is greater than 0. What do you expect? This will be greater than equal to 0, correct. So that means this is greater than, and that proves, you will notice basically whatever results we have proved, we are using it quite a bit. So you have to, like as I said, the first 2 lectures are very, very important. If you are not following any result, please ask me, because you will see whatever we are covering here in the initial lectures will be repeatedly used in subsequent lectures. Okay. So this is summation is positive. So then for this to be greater than equal to 0, this has to be more than this, and that is my log sum inequality. Okay. Now let us see an application of this. Where are we going to use this? I am going to show now the function divergence is a convex function. Okay. In fact, this result will make use of the 2 results. I have already defined what is a concave or convex function when I talked about Jensen's inequality, and I just now proved log sum inequality. So I want to show that divergence is a convex function. Now what is divergence is a function of these 2 distribution p and q, correct. Now I am using this third definition which I showed you. Remember I had showed you a definition where I showed this. If it is a concave function, then it takes 2 values x1 and x2, then lambda times f of x1 1 plus lambda times f of x2 should be less than equal to function expected value. Now if this is, I have to show this is a convex, then I have to show greater than equal to. I am going to use this form to prove. So this is precisely what I have here. Now, the left hand side there was lambda times. So I am defining, so it's a function of P and Q. So my x1 is P1 Q1 and x2 is P2 Q2. So I have to show that lambda times function of at x1, which is divergence of P1 Q1 plus 1 minus lambda, that f of x2, which is divergence of P2 Q2, that is greater than equal to function, which is the divergence function, and I had lambda times x1 plus 1 minus lambda times x2. So here it will be lambda P1 plus 1 minus lambda P2, divergence between that, and lambda Q1 plus 1 minus lambda Q2. So I am going to, so in other words, what I am saying is, to show that it is a convex function of P and Q, if I can show this holds for all lambda which lie between 0 and 1, then I have proved that divergence is a convex function of P and Q. Okay. Now, to prove this, I am going to make use of log sum inequality. Now, what I have done, now just go back to this thing. It says summation ai log ai bi, that is greater than summation ai log summation ai and bi. So I have to find out what is my a1, what is my b1, what is my a2, what is my b2. Okay. So here, what is my a1? Lambda P1 is my a1, you are absolutely right, that is my a1. What is my a2? 1 minus lambda P2, that is my a2. What is my b1? Lambda Q1, that is my b1. And what is my b2? 1 minus lambda Q2, you are absolutely right. Now, once I have identified what is my a1, a2, b1, b2, I am going to use this, that summation ai log summation ai bi is less than equal to summation of ai log ai bi. So look at the right hand term, I have summation of ai. So summation of ai will be a1, a2, correct, and then I had log of summation ai. So log a1, a2, b1, b2. So this is my right hand side here. Are you guys with me? Now this has to be less than this. So a1 log a1 b1 plus a2 log a2 b2, right. So this I get by applying log sum inequality. Now let us sum this over all possible values of x. If I sum over all possible values of x, okay, what is this term? This is a divergence of this and this, which would be this one, and this will be lambda summation pi log pi qi. This is lambda divergence of p1 q1, and this will be 1 plus lambda times summation p2 log p2 q2. This will be divergence of p2 q2. So then what I have shown is this, and if I have shown this relation, that means it is a convex function. So you can see this result illustrates, I have used both the results properties of concavity convexity and log sum inequality. am just going to show you a very small result. The binary entropy function that you have seen is a concave function. And again, I am going to make use of the result which I have already proven. I showed divergence was log L minus h of x, right? So I use that result, and I just not showed you that divergence is a convex function. So if divergence is a convex function, what will be minus of divergence? That's a concave function, and this is a constant function. So this will be a concave function. Okay. Again, there are, you can just prove this from the scratch also, perfectly fine, but since we already had these results, I just used that. Okay. So this I have proved that this binary entropy function that I showed you is a concave function in P. Okay. Now let's come to the third result, which is known as data processing lemma. So when x, y and z forms a Markov chain, then mutual information between x and z is less than equal to mutual information between x and y, and mutual information between x and z is less than mutual information between y and z. So when x, y and z forms a Markov chain, we know that probability of z given x and y will only depend on y. Okay. So in terms of entropy, we can write entropy of z given x, y will be entropy of z given y. Now let us compute the mutual information between y and z. So from the definition of mutual information, this can be written as uncertainty in z minus uncertainty in z given y, right. Now I know uncertainty in z given y is given by uncertainty in z given x, y. So I get this. Now I am replacing this by h of z given x and making it a sign greater than or equal to. Can you tell me why? Exactly. Remember, I have shown you a result which says conditioning cannot increase entropy. So uncertainty in z given x, y is less than or equal to uncertainty in z given x, because this is condition on x and y, this is only condition on x. So this quantity is greater than or equal to this quantity. So if I am subtracting a equal or a greater quantity, then this will be greater than or equal to. Okay. And what is this? This is from the definition of mutual information. This is mutual information between z and x or x or z, the same thing. So what I have shown you is, if x, y and z forms a Markov chain, then mutual information between this is less than equal to mutual information between this. Correct? Now the second result which I asked you to show was this. So I have shown you this. Mutual information between x and z is less than or equal to mutual information between y and z. Now I have to show mutual information between x and z is less than mutual information between x and y. Okay. I have shown basically if x, y and z forms a Markov chain, then mutual information between x and y is less than or equal to mutual information between y and z, right. I now have to show mutual information between x and y is less than or equal to mutual information between x and y. Now, sorry, 1 second. This is x and z, right? mutual information between x and z. So, I have to show that mutual information between x and z is less than or equal to mutual information between x and y. Now, I want you to pay attention to this form. When x, y and z were form Markov chain, we could show that mutual information between this is less than equal to mutual information between this. So, to prove this result, what do you need? If I can show you this, if I can show you that this implies this, then using this result, I will show that mutual information between x and z is less than mutual information between x and y. That is what I am supposed to prove. So, what I am going to do to prove the next result is, this implies this. I know this, but when this is there, this implies this, and if it implies this, then this result follows from the result we have just now proved. So, we are going to show that z, y and x also forms a Markov chain. So, obviously, we have to show that probability of x given y z is probability of y given probability of x given y, or in terms of entropy, entropy of x given y z is equal to entropy of x given y. So, to prove this, we are going to apply first chain rule to this joint entropy of x, y and z. So, entropy of x, y and z can be written as h of y plus h of x given y plus h of z given x y. Now, x, y and z forms a Markov chain. So, z given y and x will be h of z given y. Okay. So, what we have shown so far is h of x, y, z is h of y plus h of x given y plus h of z given y. Now, I am writing this in another way. How? Again I am applying chain rule, but in a different way. So, h of x, y, z can be written as h of y plus h of z given y plus h of x given z y. Now, both are same, right? So, equate them. This is same, this is same, this is same, this is same. What do I get? H of x given y is same as h of x given z y. So, if I compute, then I get this, which is equivalent of saying probability of x given y z is probability of x given y. So, knowing y and z, x only depends on y. That means z, y and x also forms a Markov chain. So, if x, y and z forms a Markov chain, then z, y and x also forms a Markov chain. Hence, mutual information between x and z will be less than equal to mutual information between x and y. So, what is the implication of this lemma? It is called data processing lemma. So, think about, look at our communication system. If you look at various blocks of a communication system, you have your raw data, you do source coding, then you have some encryption, you have channel coding, modulation, you send it over a channel. So, if you look at output of each block, given previous block, it only depends on the input to that particular block. Let us say if I want to look at the output of a channel encoder, right, it will depend on what the input to channel encoder is. Given that I also give you the input to the source encoder, if I specify just the input to the channel encoder, that is good enough. So, in communication system, various blocks, if you look at output of each block as some random variable, they form a Markov chain. So, what it is saying is, if you do further processing of the data, because x is like initial and z is the final output. So, mutual information, the information content is getting lost in some sense, like information theoretically further processing of data, actually you are losing information. Whatever information y is giving about x, z is giving less information. So, further processing of the information, from the information theoretic point of view, you are losing information content. But then why are you then doing it if you are losing information? Because we are putting the signal in a form which is easy for the receiver or this thing to basically. So, from the information theoretic point of view, when you do further processing of the data, you are actually losing information. That is the application of this data processing lemma. Okay. Now, we will move to our final lemma which we are planning to prove here, which is Fano's lemma. Again, this is a very useful lemma. It is used in proving the converse of many theorems, and it relates probability of error to the estimates of the random variable. So, let u hat be the estimate of a random variable u. Now, when u hat is not equal to u, we know there is an error, and when u is equal to u hat, we receive the bit, we estimated the bit correctly. Okay. So, let u and u hat be an LRE random variable, that means they take L possible values, okay, and probability of error is defined as this. So, when u is not same as u hat, there is an error. Then we can show that binary entropy function of this probability of error plus p log L minus 1 is greater than equal to uncertainty in u given u hat. Okay. So, this is a result which basically relates probability of error to this uncertainty in u given u hat. Okay. So, let us prove this, and of course, this equality holds when these two conditions are met. The first condition is, if the probability of error given u hat is u is same for all u, and if there is an error, all L minus erroneous values of u are equally likely to happen. When these two conditions are met, this is an equality. Okay. So, let us first prove this result, and then we will revisit and see where we have put inequality sign and when are those inequality signs are satisfied with equality. So, we are defining an indicator random variable. Now, what is an indicator random variable? It indicates whether there is an error or not. So, when there is no error, the value of this indicator random variable will be 0, and when there is an error, the value of this will be 1. So, z will be 0 when u and u hat are same, otherwise z will be 1. Now, uncertainty in z can be written as binary entropy function of P of E. How do we get this? Z takes two values, 0 and 1, right. What is the probability of 0? 1 minus P. And what is the probability of 1? P. So, then what is the uncertainty in Z? Minus 1 minus P log of 1 minus P and then minus P log of P. So, this follows from how we are defining this indicator function. H of z is equal to h of p, because z is 0 with probability 1 minus p and z is 1 with probability p. So, uncertainty in z is uncertainty in p. Let us compute uncertainty in u z given u hat. Now, this can be written as h of uncertainty in u given u hat plus uncertainty in z given u hat. Now, what is the result that we have used here? Chain rule. We basically applied chain rule to get this, correct? Now, what is the uncertainty in z given u and u hat? Z is a function of u and u hat. If I tell you what u and u hat is, you know, so you can find out whether they are same or not. If they are same, z is 0. If they are not same, z is 1. So, given u and u hat, you know exactly what your z is. So, then there is no uncertainty in z knowing u and u hat. So, this will be 0. So, what I have shown is uncertainty in u z given u hat is equal to uncertainty in u given u hat. Now, I am just using this same result. Uncertainty in u given u hat is given by this, right. Now, this can be written in this particular form: uncertainty in z given u hat plus uncertainty in u given u hat z. This follows from chain rule. I have applied chain rule in a different way. So, this follows from the chain rule. Now, I have put here h of z given u hat is less than equal to h of z. This follows from the fact that uncertain conditioning cannot increase entropy. So, h of z given u hat is less than equal to h of z. Now, we are going to calculate this h of u given u hat and z. So, to compute this, what I am going to do is, I know z takes values 0 and 1. So, I am going to compute h of u given u hat and z equal to 0, and similarly going to compute h of u given u hat and z equal to 1. Then how do I compute this? This will be nothing but probability of z equal to 0 multiplied by the uncertainty in u given u hat and z equal to 0 plus probability of z equal to 1 into uncertainty in u given u hat and z equal to 1. So, this is what I am going to do. So, I am saying uncertainty in u given u hat and z equal to 0 is 0. Why? Exactly, when z is equal to 0, u is equal to u hat. So, since u hat is given and z is 0, you know what your u is. So, there is no uncertainty. So, given that z is equal to 0 and given u hat, you know precisely what u is. So, there is no uncertainty. Okay. Now, I have also written uncertainty in u given u hat and z equal to 1 is upper bounded by log of L minus 1. So, what happens when z is equal to 1? There is an error. You have been given u hat and there is an error. So, I can say that u is not u hat. So, out of those L values, I know one of them is not there, u hat is not there. So, u could be any of the remaining L minus 1 value, and we have proved a result that if x is a random variable which takes L different values, then maximum entropy is log of L. So, here my u can take L minus 1 value, because I know there is an error. So, it is not u hat. So, it can take any of the remaining values, L minus 1 value, right. So, this is then upper bounded by log of L minus 1. See, that is why I was still telling you all the results which I have showed, we are revisiting them again and again to prove the result. So, what I have shown here is uncertainty in u given u hat and z equal to 1 is less than log of L minus 1, correct? Now, we know this, we can compute uncertainty in u given u hat z, which is nothing but probability of z equal to 0 multiplied by this, which will be 0 because this is 0, plus probability of z equal to 1 multiplied by this. Now, what is the probability of z equal to 1? Z equal to 1 meaning there is an error, that is probability of a, so that will be P. That is the probability of error. So, we have shown that uncertainty in u given u hat z is upper bounded by P log of L minus 1. Now, if we plug that in here, basically we will get here, this is upper bounded by P log of L minus 1. Okay. Now, this proves our result. Why this proves our result? We have what is h of z e, that is P of E. This we have shown is upper bounded by P log L minus 1. So, then h of P plus P log of L minus 1 is greater than equal to h of u given u hat, and that was our Fano's lemma. Okay. Now, let us show, we said the equality holds if and only if these two conditions are valid. If and only if probability of error given u hat is u is same for all u, that is the first condition, and second condition is if there is an error, all L minus 1 erroneous values of u are equally likely. These are two conditions that I am stating, right. So, first condition says probability of error given u hat is u does not depend on what u hat you have chosen, it is same for all u hat. Now, look at first place where we encountered this. Uncertainty in z given u hat is less than equal to uncertainty in z. What is z? Z is an indicator function saying whether there is an error or no error. Now, if it does not depend on what the particular value of, it is same for all u, it does not depend on a particular value of u hat, this would be equal to this. So, that is the first condition I said. Equality holds if the probability of error given a particular u hat is same for all u. So, h of z given u hat would not depend on what a particular u hat is, it is same for all u hat. In that case, h of z given u hat will be equal to h of z. Now, what is the second condition? All L minus 1 erroneous values of u are equally likely. Now, see where we are using the next inequality, that is here. Now, if you recall, when x is uniformly distributed, h of x is log of L, all possible values. I am saying h of u given u hat and z equal to 1 is less than equal to log of L minus 1. When is it equal to log L minus 1? When all other values are equally likely to happen. So, that is the second condition that you are getting. So, equality holds if probability of error given u hat is u is same for all u, and if there is an error, all L minus 1 values of u are equally likely to happen. Okay. So, that is your Fano's lemma. In some places you will see some small variants of this, somewhere you will see h of p plus p log of L minus h of u given u hat. Some places you will see, because h of p is upper bounded by 1, you will see 1 plus p log of L minus 1 greater than equal to h of u given u hat, or you will have 1 plus p log of L greater than equal to h of u given u hat. So, those you can derive from this particular form. It is a very, very powerful lemma, and it is used in proving the converse of channel coding theorems. And so, it is basically when you have to prove things like, okay, we want to show that if you try to communicate at a rate greater than capacity, then probability of error is non-zero. That means we want to show that you cannot communicate at a rate greater than capacity. So there we have to show that if the rate is greater than capacity, then probability of error is non-zero. We make use of Fano's lemma there. So all those converse theorems essentially uses Fano's lemma, and you will see a lot of them in this course basically. So I hope I am able to convey to you some of the important inequalities, starting with Jensen's inequality and log sum inequality, and then data processing lemma and Fano's lemma. You will, as we go around in this course, you will see more applications of this course, these inequalities. Okay. So with this, I will stop here, and if you have any questions, I will be happy to answer. Okay, thank you.